Welcome to the lecture Philosophy of Science in Introduction. In the last unit I spoke about the value neutrality of the sciences, and during this course, I gave you a classification of scientific disciplines according to the objects of investigation. Today I start with a brief mentioning of further possibility of classifying scientific disciplines, which may be interesting, and which is the following. It's a classification of the factual sciences, so to speak, according to the intensity of their invasiveness into the objects of investigation, according to the intensity of their invasiveness into the objects of investigation. So the big light gray circle and everything which is in this circle, including the darker gray areas here, this represents the set of all empirical disciplines. The set of all empirical disciplines according to our criteria, which we have set up in the last units. So the epistemological assumptions which are common to the sciences, the methodological features which are common to all sciences, and the goal of the science, of course. Outside of that are the so-called speculations, so like theology, human ideas which are based on dogma or on creed, but not on the method of empirical sciences, right? Now this light gray circle, the largest circle here, includes also all the empirical sciences in the field of the humanities, right? Which are, for instance, history, whose data are based on historical records, on archaeological findings, and on literary sources, etc. Okay, the smaller circle in medium gray here represents the experimental sciences. So the experimental sciences are those sciences which are able to make controlled experiments, right? So there is, for instance, typical for psychology, right? The difference here is that between field observation here and experiments here. The difference is that in field observation you just observe what's going on without intervening. You do not intervene. You do not put the object of investigation under certain conditions. This is exactly what you do in an experiment, right? You put the object of investigation under a certain condition by intervening, by manipulating it, in order to find out what happens under these certain conditions which you want to observe. But you don't wait until by accident this rare condition happens to be observed, but you produce it by intervening. That's an experiment. For instance, if you want to find out something about how rats learn, right, you can do it by field observation and study years, right, of rats and what they are doing, right, in their natural environments, in canal systems or whatever, in the rural area, and so on. But if you do experiments, you put them into a lab, you put them into an artificial environment, for instance in a labyrinth or in a certain system of labyrinthic system of path, and see which path the rat takes under certain conditions, if she smells something, and so on. So this is an experiment. And the advantage of experimental research opposed to field observation is, of course, that in order to find out which in order to find out which was the cause for a certain effect, right, you have to vary the conditions of your environment one by one, right? So if you, for instance, have an allergy, right? You assume you have an allergy and you want to find out what is the cause of my allergy. The fastest way to find that out is to vary your conditions one by one. Is it your nutrition? Then you should vary your nutrition, but don't vary other conditions like where you live, which household you live, and which geographic area you live. Or is it the plants outside of in the area where you live, the trees and so on? Then change the place where you live, but don't change the nutrition at the same time, right? Only change one factor. Or is it maybe the dust in your household and the dirt in your household? Then clean up your household, but do not at the same time change your nutrition or change any other factors. So by systematic variation of factors, you can find out which of the changing factors was causally relevant for the effect. And the person who introduced actually this method in the philosophy of science is a famous philosopher of the 19th century of the name of John Stuart Mill. So if you cannot do this, if you cannot artificially manipulate the conditions in the form of an experiment, of course it's bad, because you maybe wait very, very long if you do only field observation for observing just that constellation which you need to find out whether something is causally relevant or not. And that's the reason why in the humanities, of course, research proceeds much slower and is more difficult than, say, in psychology, because, and this is the other side of the story, because, of course, you cannot do experiments in all fields of sciences. You cannot do experiments with large social groups. You cannot, on ethical reasons, on practical reasons. Although in education science, you cannot do really experiments with pupils, giving them a very bad, like, teaching curriculum and seeing whether this bad teaching curriculum, to which extent their cognitive achievements will decline, right? Or you cannot artificially put humans under painful conditions to find out what's going on when you put pain on them. So even in psychology there are certain limitations of experimental possibilities, right? So this is an important difference here between those sciences which do only field observation, right, and those sciences which can do experiments. Good. But there's this inner core of sciences which are the classical natural sciences, like physics, chemistry and biology, which do even more than the experimental sciences, right? Namely, I call them dissecting sciences because what they do is they really cut and dissect, right, the objects of their investigation materially into their pieces, and try to understand the law which describes the behavior of their pieces, of their parts. And by understanding these laws, they intend to synthesize the objects then again from their pieces. So if you really are able to do this materially, to deconstruct the nature, the objects, the material objects of your investigation into their smallest parts, atoms, and then compose them from them once again successfully, so that the same complex atom is created, then you really can say that then you have the fullest kind of understanding of nature, right? But of course also with this method a lot of potential dangers are going with it, right? Because your power now to manipulate nature has increased. But this is typical, right, for the classical natural sciences which goes beyond experiments. In experiments, like psychology, you ask people certain test questions, you put them into certain situations. That is experiments. You put rats, like in a certain lab, into a certain situation. But you don't dissect the rats or cut them into pieces and look directly what's going on with the brain. So that would be what I mean with dissecting sciences, if you really look inside the object. So in chemistry, for instance, that method is absolutely successful. You find out what are the molecules which constitute the given substance, for instance, an organic substance. You find out the atoms which constitute the parts of these molecules. Then you the method of material analysis in chemistry is called analytic chemistry. Yeah? You compose the molecules into the smallest atoms. Then you know the structure of the molecules. And synthetic chemistry is called that discipline where you then synthesize the complex molecule once again from the atoms. And you know many natural substances in organic chemistry which you find in nature, like all food substances, ethers and so on, are nowadays, in the meantime, it's possible to synthesize them, and they are indistinguishable from the natural counterparts, right? Some people don't believe it, but it's true. I mean, the food ethers which you have synthesized taste exactly like the food ethers. Ethers is a certain chemical substance. The esters, so to speak, which are which are in the natural plants, right? So the same is going on in say nuclear physics, where you really are able to decompose atoms into smaller parts. This is called. This is going on in atomic plants, in nuclear reactions, in atomic decays, and nuclear fusions, right? Where you fuse certain nuclei to get larger atoms, which is going on, for instance, in the sun or in all experiments involving nuclear fusions. And you know that huge amounts of energies are set free by these processes, which of course is a high danger. And if you think what this idea of natural sciences, the dissecting sciences, implies for biology, or if it would once be applied to psychology, it is already a little bit applied, then it would mean to decompose materially the human being into smallest parts, right? Genetic engineering, for instance, and to synthesize a new being, right? Something like a perfect human or whatever, right? So the possibility of altering the genetic code of humans would of course all be within this program of applying the method of dissecting sciences, say, for instance, to biological organisms, including human beings. And it's clear that, well, in some sense, this is already done, and it's, of course, it's ethically problematic too. There are a lot of dangers involved of that. And as always, following from the value neutrality thesis, which I taught about last unit, you can apply sciences, right, in that or in that direction. The application of sciences is, of course, depending on external values. And, of course, you can do a lot of good things, too, with genetically altered plants, which are growing faster, which have much more advantages, by which you can feed a higher population with less ecological costs, for instance, right? But you can, of course, also do bad things and ethically problematic things with all kinds of genetic engineering. So one thing is clear. The more these kinds of sciences, these are the most effective ones, but also the most problematic, and the more these are evolving, the more the discipline which is called the ethics of science becomes important. So far, and so much about this threefold division of sciences. Any questions to this part? Or additions? Comments? Nothing? Yeah?
It's just a comment. It seems that in some research fields, scientists make use of all these methodological steps. For example, in biology, if you're interested in plants, you can look into an area and, for example, count the plants. If you're interested in the distribution of the plant, and you also can dissect them when you're interested in a certain concentration of materials within the plant.
Thank you. This is a very good...
The science is rather research-oriented here.
Mm-hmm. Well, thank you for this comment, which is very good, a very good complementary comment here, because yes, there are certain fields where all these three procedures are important. In biology, you do field observation. Like, that's how Konrad Lorenz started. He observed the gooses in the field. But then he did already little experiments with them, trying how they react if he, the role model of the gooses, does this or that. That's already an experiment. And then, of course, in biology also, you dissect. That's where the notion of dissection comes from, right? You dissect the organisms. And also in medicine, of course, you dissect dead human bodies, starting in the Middle Ages. It was important for the development of medicine and for the progress which was made, this dissection. But you do all three things there, right? Yeah. Good. So, let me finally mention a further division and classification of sciences, namely, which is also useful and common in philosophy of science and methodology, namely the distinction between qualitative disciplines and quantitative disciplines. There is a distinction in social science called, well, there's qualitative research and quantitative research. Qualitative research, for instance, is taking place when you do field observation, field research, right? In social sciences, when you, for instance, want to know what are the important ideals and idols and the important lifestyles of youth, of young people in Germany, and you have no clue where you start with your investigation, and you start with qualitative research. That means, for instance, you don't start with a multiple choice questionnaire, because you don't know what the relevant questions are, but you make a so-called free interview where just the people tell something, you ask them questions and they just tell you a story, and that is a qualitative interview that to tell you what's important for them, and then you collect certain clues, which is the ideas and the ideals, the criteria which are important for the image, for having a good image of young people, what they like to do in their free time, and so on. You get a lot of clues in this qualitative research, in these free interviews, and if you have done that, so there is not much statistical or numerical methods involved here, but if you have done that, then you can set up a quantitative experiment, so to speak, or a quantitative research, by setting up a multiple choice questionnaire, where then ask precise multiple choice question, from which you then get a certain statistics. So many percent of young people make sports, so many percent of young people go to parties, have friends, so many percent of young people spend most of their free time on the internet or with computer games and so on. So you see that my point of view on the relation between qualitative and quantitative research is not so much that of a competition, as some persons see it, but more as a kind of division of labor. In the in the pre-stage of research, it's more a qualitative research question, and in the more advanced stages of a research project, you apply the quantitative methods. So both have their place in science, and both are needed in science. There's no argument that qualitative methods would, in some sense, be less scientific than quantitative methods. They are just applied for different purposes and in different stages of research. So much on this distinction here. Any questions on this? Oh. Good. If not, then I proceed. I come now to the next section of my talk, of my lecture, and this is a section of methods of reasoning and argumentation in science, right? Kinds of inferences in science. So this is a new chapter. So let me start with this observation. Recall these common foundations of the sciences where we had these methodological features. And recall we had these methodological features M3 and M4, right? So we had this general hypothesis, and we had this what we called observations, right? And we said in this feature M3 the scientist attempts to explain by means of his general hypothesis the data, the observations he or she makes, and to predict new potential observations, so to make empirical predictions. And then the scientist in M4 compares the predicted observations with the actual observed observation, and if they agree, the hypothesis is confirmed, and if they don't agree, the hypothesis is confirmed or falsified. And this goes on in the methodological feature M4. Right? So in the methodological feature M4, the scientist infers. So in the feature, let's start with M3. In M3, the scientist infers from his hypothesis something about the observations which he will make. And in M4, the scientist infers from the observations something about the hypothesis. Here, the scientist infers that if the hypothesis and the assumptions are true, then certain observations will be made. Here, the scientist observes that if the observations which have been made are those which the hypothesis predicts, then the hypothesis is confirmed, right? And in the other way around, if that not happens, it's weakened, disconfirmed. Both are inferences, as you say, but these inferences are very different in nature, and that is what I'm speaking about now. What are these kind of inferences which are involved in these procedures? And there's a very classical scheme which gives the first answer, the most simple answer to our question here, and this goes back to Aristotle, and this is called the inductive deductive schema. So this schema says, from the general laws and theories you deduce something about the particular. From the general you infer to the particular by means of a deduction, of a deductive inference. So this is also called the deductive descent. Now, this is deduction. And from the particular, from the observations, right, this and that, this data, you infer something about the general, the laws or theories, by means of induction. Induction here, inductive ascent. Ascent. Right? So this is the inductive-deductive schema. And these two inferences, deduction and induction, is what we speak about now here. And you will see they are quite different. Okay. And you will also see that Aristotle's schema is way oversimplified, right? But it contains, it's what it says, it's correct in its core. But it's oversimplified. Okay. So let's go on. First of all, in this schema, induction is something which I call induction in the broad sense. I will explain to you soon this induction in the broad sense, by which you mean every inference from a particular from particular observations to something, a general hypothesis. If you call every inference of that sort induction, then this includes induction in the ordinary narrow sense, as will be introduced now, and something which is also called abduction, or inference to the best explanation. Both is included in this general notion of induction in the sense of Aristotle. But we make this differentiation here on some important reasons, right? We differentiate here. Okay. So actually there are three kinds of scientific inference and argumentation then. Deduction, induction in the narrow sense, and abduction, as we will see soon. First of all, let me explain what is the crucial difference between induction and deduction. So, let me start with, here is it, deduction versus induction. The key feature of deductive inferences is that they are certain. It is certain that if the premises are true, then the conclusion will be true. In all possible worlds, as one says, the truth is transferred from the premises to the conclusion. For instance, all ravens or all raven are black. This is a raven, therefore this is black. This is a deduction, right? So, I mean, you are not sure whether really all raven are black, right? But you know, so the correctness or the validity of a deductive inference is not dependent on whether the premises are true, right? But if the validity means the certainty, the deductive certainty means that if all ravens are black, and this is a raven, then this animal must be black. Because if it wouldn't be black, and it would be a raven, then the first premise would have to be false. Yes. That's clear, right? So deductive logic is certain, and this makes up what you also call logic in a narrow sense. I mean, it's not the case, and this is a first simplification. This is the second simplification in Aristotle's models. The first simplification is that there actually is induction and abduction here, but the second simplification is that not every kind of deduction is an inference from the general to the particular. Here this is an inference from the general to the particular, right? If all raven are black, then every raven which I observe must be black. That is a test of this hypothesis, right? This inferences. If this is a prediction, then it's a test. But there are also inferences, say, there are also other kinds of deductive inferences. For instance, there are inferences from the general to the general, right, which are deductive. Does one of you know, or can one of you tell me such an inference from the general to the general? For example, yeah.
All ravens are black. All black things are not white things.
Exactly. Thank you. So this is actually in Aristotle's syllogistics. That's the inference called modus barbara, right? All A's are B's. All A's are B's. Thank you. All B's are C's. Therefore, all A's are C's, right? All A's are C's. This is, for instance, a deductive inference from the general to the general. A nice example, all ravens are black, all black things are whatever, not white, therefore all ravens are not white. Yeah. And of course, there are also deductive inferences from the particular to the particular, right? For instance, this raven say A and BA, therefore AA. So I put that symbol here. So this is a raven, and this raven is just picking a nut, right? Therefore, this is a raven, right? Simplification. So there are a lot of deductive inferences. Not all of them are going from the general to the particular, but of course for the method of scientific testing it's very important. These inferences which are going from the general to the particular, or actually, as in this example, this is also simplification, right? They go from one general premise and one particular premise to a particular conclusion, right? So these inferences are most important for scientific test procedures when you test a strict hypothesis. Okay. So much about deduction and deductive inferences. Now what is induction? Well, induction is, opposed to deduction, it's uncertain. In an inductive inference, right, and I first discuss the inference of inductive generalization. It's possible that the premises are true and the conclusion is false. For instance, here the form of this inference is all A's observed so far were B's, therefore all A's are B's. Well, this is plausible, right? But of course it may be false, because from the individuals which we observed so far, we cannot logically infer something about the individuals which we did not observe. We can make this inference only if you assume that our world is what we call uniform, is inductively uniform, so that the past resembles the future. The past observation resembles what we will experience in the future. The individuals which we have observed resemble the individuals which we have not observed, right? You call this also in statistics the requirement of representativity. The individuals which make out our test sample are representative for, in the case of generalization, what you need is for the total population. They're representative, right? And what that exactly means will be spoken about in this lecture in 5 units from now, because it's not so easy. But it's clear, generally speaking, only under these conditions inductive inferences are reasonable, right? And otherwise they aren't. So in this case, for instance, let me write it down. You have the inference, for instance, it would be the inference going from all raven observed so far they are black, therefore probably, that's why I put that in brackets now, probably, and probably means just a degree of belief, something very vague, right? It's probable, it's plausible. All raven are black. All raven are black. And if I make a double stroke here, then I indicate that this inference is uncertain. I mean, whether this inference is reasonable depends on how you produced your sample. I mean, if you just observe ravens, right, in a particular location, not on a random sample of places on the whole Earth, right, where ravens occur on all continents, then of course it's quite very uncertain. This inference is then very uncertain, right? It has a high chance of having true premises but a false conclusion. But if the observation sample is really representative, then the chance of having a true premises and a false conclusion is smaller. But only smaller given that the world is uniform, right? And what uniformity means is itself very difficult to explain. The statistical version of induction is of the inductive generalization inference. It's this one. R% of the observed A's were B's, therefore approximately R% of the A's were B's. So, for example, 70% of the observed German people in this test sample were brown-eyed, therefore probably approximately 70% of all persons in Germany, of German people, are brown-eyed, right? Have brown eyes. So sometimes you also specify a so-called confidence interval. This means here plus minus epsilon. So R plus minus a small value, like between 68 and 72% are brown eyes. So this is a statistical counterpart of this inductive generalization inference. Okay. Yes?
So the statistical version is not a limiting case of the first version, right? Because the first version doesn't include this error parameter.
I would say so, yeah. So it's not so easy, right? I mean, if you really, if you strictly all A's observed so far were B's, then you conjecture, well, this might be a strict law of nature without exceptions, and therefore you have here the probably, but you don't have an interval here, because either it's strict or it's not strict. On the other hand, if you have strong reasons to suppose that this is not a strict inference, right, but you have so far observed only A's that were B, you might even include a small epsilon interval here. But it would then be an asymmetric interval, so the usual statistical method of Gaussian curves wouldn't apply, because it's at the one side of the value space, so the interval would be left asymmetric, and maybe we come on this topic in later sessions, but that's already now then advanced statistics. Right. But there are inductive, if you have there are inductive systems which first have the distinction, have the decision, is it a strict law, probably or not, and if it is, then you have this inference.
There's a separate problem with the first type.
It's a separate problem, yeah. Okay. So, inductive predictions are a second kind of inductive inference. All A's observed so far were B's. And now you don't infer inductively from your observations to the full population, to the entire domain, but you just observe to arbitrary future instances that will be observed. So you infer, therefore the next A will be B, or it will probably be B. I don't speak here about the details now about the statistical version of that. Okay, so this is induction. Now, we might ask, if inductions are uncertain, can we say under which conditions? Well, we said it already, that under certain conditions they are reasonable, namely if the future resembles the past, but we don't know the future, right? Can we justify without knowing anything about the future, that inductive inferences from the past to the future are reasonable without knowing anything about the future. Thank you. And here the question is very difficult, and the answer is, so far in philosophy there is no good answer to that question, because the problem here is called Hume's problem of induction. Hume's problem of induction. David Hume in the 18th century raised this deep problem: how can we rationally justify inductive inferences? So think about inferences from the past to the future without knowing anything and without presupposing anything to know about the future. And his answer was, we cannot. So there is no, basically there is no non-circular justification of induction. Because Hume argued that whenever we want to justify that the inference from the past to the future is reasonable, is plausible, leads to true conclusions from true premises in many cases, then we have to assume something about the future, right? But we can only know about the future by means of an inductive inference. So we end up in a circularity, right? However we argue, we might argue, inductive inferences are reliable, are reasonable, because so far in the past inductive inferences were reliable. Therefore by induction they will be reliable in the future. But then we presuppose induction and have a circular reasoning which is of no justificationary value. Or we may argue inductive inferences are reliable because they are laws of nature which tells us that the future will resemble the past. But these laws of nature can only be justified by means of an inductive inference, and therefore again we end up in a circular reasoning which is of no justificatory value. So this is basically the problem which Hume set up and which is called Hume's problem of induction. Now I will not speak a lot about Hume's problem and ways how one might solve Hume's problem of induction in this lecture, because that belongs not so much to philosophy of science but to epistemology. Several ways have been suggested to how induction can nevertheless be demonstrated to be somehow reasonable. For instance, ways where you don't show that induction will be reliable, but you show something weaker, namely that induction is the best what we can do if we want to make predictions. Like, yes. So this was an argument which goes back to Hans Reichenbach. He called it the argument of the best alternative, and personally I was working on this method of justifying induction too. I call this the optimality justification of induction. So although you cannot non-circularly demonstrate that the future will resemble the past and therefore inductions will be reliable, you can nevertheless argue that induction is the best what we can do at all. In a certain sense, the best, right? What we can do at all when we are under the pressure to predict the future based on the past, right? So it's not so that there are no chances to solve somehow or to give at least partial solutions to Hume's problem of induction. But it's a controversial question in philosophy. And some philosophers think that Hume was basically right, that there is no good solution to the problem of induction. Anyhow, the major question which is interesting for us here and now in this lecture is to which extent sciences really need the method of induction. And I will argue in a minute that induction is really very important inference in the sciences. Okay, so you have a question?
Yeah, I was about to ask what you think about the critical rational solution, but maybe you...
I come to that in a minute. This was not just a preparation stage for the critical rationalists, right, which I will speak in a minute. But before I come to that, I speak now about the third kind of inference in the sciences, which is abduction, or inference to the best explanation. So abduction or inference to the best explanation. So abduction is also called inference to the best explanation, or you may call it inference from an observed effect to an unobserved cause, right? Which may be, so to speak, a theoretical entity. So here's this general schema. This is an A. These are the premises here. This is an A, is the first premise. This fact that it is an A can be explained in the given background knowledge by the assumption that this is a B. This is the second premise. It's a complex premise, right? It depends on a certain background knowledge. Therefore, conjecture. This is a B, right? So this is a general schema. And if this inference is an inference to the best explanation, then you should add here this explanation which can be given is the best explanation which is available in your background knowledge, right? So example, I hear the sound of a dog barking outside the door, right? A. Can be explained that there is actually a dog outside the door now barking. This explains why I hear the sound. Therefore probably there's a dog outside the door barking now, right? And also it's the best explanation because of course there could be a radio, a tape recorder, right? Someone who likes to produce sounds of barking dogs going with a tape recorder all around. But this explanation is much less probable, therefore I don't infer that there is a tape recorder with a barking dog outside of the door if you hear a barking dog, but I infer that there's a barking dog, right? There could also be a person who is imitating barking dogs, right? But I don't infer that. So that would be an improbable explanation. So you see, this kind of inference is something which is very important in common sense, in everyday life, right? As well as in the sciences. It's an inference from observed effects to unobserved causes, right? It's very important in science, and it is not really induction in the narrow sense, because, you know, I don't generalize what I observe here. I observe sounds. Induction in a narrow sense would be to generalize something about sounds, right? Whenever I hear this and this sounds, I have this and this experience, and I generalize this to the future. But here I infer from the sound to the dog, right? Which is a very different inference. Still, this inference is quite harmless, right? Because, you know, I can observe dogs, and I have observed dogs before. It's not unobservable in principle, a dog, right? It's just now that the dog is on the other side of the door, so I can't see anything, right? But I could open the door and look. Yes, there is indeed a dog barking, and so this would be the confirmation. So therefore, Charles Sanders Peirce, that already said that abductions are really very uncertain. It's just a method of conjecturing a plausible hypothesis, and they have to be put under subsequent test then. For instance, in the dog case, I open the door and look, I hear the barking sound, I open the door and look, is there really a dog? If yes, then it's confirmed. Okay. At this point, let me mention two names. Charles Sanders Peirce was a famous philosopher, right, in the 19th and 20th century, and he coined the term abduction and introduced the method, the inference of abduction. And later on in the 1965 paper, it was Gilbert Harman in a 1965 paper who introduced the notion of inference to the best explanation referring to Schurz and Schurz, and just, so to speak, making something explicit which was already implicit in Peirce's notion of abduction, namely that the explanation which the abductive inference generates, right, should be the best available explanation which one has in the given background knowledge, and which is quite obvious. So this is this kind of inference. As I said, in the case of the dog who barks and whose sound I'm hearing, the situation is easy because there is an easy test. Just open the door. But in science, what is important, by means of abductive inferences you create also theoretical models, right, about unobservable entities, like for instance, I will speak about that later. For instance, Isaac Newton, right? Isaac Newton, but I mentioned it right now. This is a theoretical model abduction, what is really important in science. Isaac Newton inferred from the movement of planets around the sun, which was observed, sun, planet, which was observed by many, many telescopic data by Tycho Brahe and many others, which is telescopes at that time. By the laws of describing the movement, accelerations, the velocities, etc., positions, direction changes, and so on, Kepler's laws, he inferred abductively that there should be a certain gravitational force which compensates exactly the centrifugal force of acceleration, and these forces, together with the second Newtonian axiom about the total force law, right? Total force equals mass times acceleration. These together explain why planets move around the sun in elliptic circles and why this trajectory is stable. So here the abductive inference infers from data, from premises about movements, a totally new entity, namely something about forces. Though you see here why this inference is really, first of all, important for creating theoretical models. Second, why this inference transcends induction in the narrow sense, because it introduces a new concept, right? A new relation in nature, namely forces, which you cannot directly observe. You cannot directly observe, right, these forces. And still they are there, and you indirectly measure them by means of inferring from certain trajectories from the movement of particles in space and time to the forces which explain them as being their causes. So this is abduction in science. Okay. Yes, question?
Couldn't this statement be explained by deduction? So that Newton set a general law about objects and the forces, so he applied it to this.
Abduction is just the inverse of deduction, right? Right? I mean, of course, the inference from force laws, the laws about forces, right, and initial conditions, this is one, this is two. Initial conditions of the planets, like the distance of the planet to the sun, to third, right, trajectory of the planet, this is a deduction, right? From 1, 2 to 3, this is a deduction, right? Okay? This is a deduction.
Okay.
But the abduction goes, is just the other way, right? The abduction goes from 3 and 2 to 1. This is an abduction. It goes from the conclusion to the to one of the premises of the deductive inference. And that was Newton's general abduction, that he reasoned from the observed phenomena here and here. This is observable. But that is not observable. This is theoretical here. So he reasoned from that and that to that. And that is, of course, an abduction, not a deduction. He then derived prediction from his hypothesis, which is a conclusion from his abductive inference, right? And these predictions he derived by means of deduction then. So you test the conclusion of an abduction then, as Charles Sanders Peirce says, by subsequent deductions and inductions applied to that hypothesis. And if they are confirmed by your observation, then then the abductive conjecture, which initially is very uncertain, gets more and more confirmed, right? Okay?
Yeah.
Yes? Good. So abduction, in terms of logic, means to infer from the conclusion of a deductive inference and one premise to the other premise. Actually, you found this already in Aristotle's notion of an apagoge inference. So this already goes also back, this idea, to Aristotle. Yes?
Couldn't you argue that inductive generalizations are also, in a way, cases of abduction? Because you might say the fact that all ravens I observed so far are black is best explained by the general hypothesis that all ravens are black.
Yes, this was the argument of Gilbert Hamann. He argued that actually inductions are cases of abductions. But the point is that in order to justify the abductive inference as reasonable, you need an independent justification of induction already. Because if there is no reason to suppose that you can generalize observed patterns, then there is also no reason to argue that the generalization is the best explanation. Right? If you don't assume that the world is uniform, then it's not clear, while the fact that so far all ravens were black is best explained by the assumption that it will always be the case that all ravens are black. I mean, if the world is not uniform, then why should that be a case, right? And the question is whether then there's an explanation of all at all. But it's not clear that the inductive generalization is the best explanation if you don't assume certain inductive principles already. So that would be my argument. Well, ultimately, there's no way to reduce this in that way. Yeah.
So you think induction is easier to justify than abduction, maybe? I
say so. Induction is hard to justify, but abduction is even more difficult to be justified. Because in abduction, in theoretical model abduction like here, you do more. You assume inductive generalizations, of course, of certain observed patterns of velocity and kinematics, as you call it in physics, movement, right, of particles. But you also introduce an unobserved concept, which goes beyond induction in the Humean sense. You introduce a notion of force. So abduction is even more at risk, so to speak, yes. So I come now to the decisive point. It is controversial in philosophy of science whether abduction is a scientifically legitimate mode of inference at all. I would say yes. I am on the side of those who say yes. But Popperians, and now I come to Karl Popper and the critical rationalist where you asked about. Now I come to Karl Popper and the critical rationalists. Critical rationalism is, at least in continental Europe, quite influential, also in UK, in English-speaking countries, maybe in the USA to a less extent. The philosopher of Karl Popper, Hans Albert, Alan Musgrave, Watkins, and several further, David Miller, and students of famous students of Popper. So Popperians say no, abduction is not a mode of inference, because an inference should have at least some justificatory value. But abduction is only a method, Popperians say, of discovery for hypotheses, right? And you could discover hypotheses, of course, by abduction. That's just a discovery method, right? But you can discover it also by trial and error, Popper would typically say, right? What is important is only this conjecture, this is a B, like Newton's conjecture, there is this gravitational force described by the gravitational force law. What is important is that this conjecture is put to test subsequently, and then by the method of deduction and induction is confirmed, right? Critical rationalists would say. Or abduction enemies, abduction opponents would say so. So abduction is a method of discovery, but by itself does not convey even not a little justification to the conclusion. It's just a method of discovery. I don't think so. I think it's more. I belong to those who think that abduction is also minimally justificatory in a certain sense. It's minimally justificatory. Of course, it's very uncertain. But that's a controversy in philosophy of science, right? And even if it is a method of discovery, I would say that Popperians are clearly wrong that trial and error is equally good than abduction as a method of discovery. Because abduction is a very intelligent method of discovery which reduces the search space for possible explanations a lot, while trial and error goes just by blind trying out something. It wanders through a huge search space, so it's much less efficient, I think, than abduction. But this is a question of its own. At least deduction and induction, the majority of philosophers would say at least deduction and induction are scientifically legitimate and essential methods of scientific inference. And all empiricists would say that, of course, most philosophers of other camps. But now look, this is a problem. Oh, oops, I would have to say here. Oops, this is the English version of oh. Popper and his student even doubt the legitimacy of induction. Right. So that is what the critical rationalists is famous for. They even, strict Popperians even say that induction is only a method of discovery and not a method of justification. Right? How can that be? Well, this is understandable by the fact that Popper was very impressed by Hume's problem of induction, and by the challenge of David Hume that there is no rational justification of induction. And Popper belongs to those philosophers who think Hume is basically right. There is no rational justification of induction. But then, if induction is the central method of science, in the sense of justification, right, then the entire method of science would be entirely unsupported and would have no rational justification. Then, like Russell once said, there would be no clear differentiation between scientific argumentation and madness, right? If induction wouldn't have a rational justification. So Popper was so impressed by this problem that he wanted to show that actually scientific practice can do without induction. Induction is only needed in the discovery stage, but not in the justification stage. And in the end of this lecture today, I want to discuss a little bit more and a little bit more in depth Popper's views on the role of induction in science. Okay. And I will try to argue here, and I will try to convince you that indeed many of the arguments of Popper against the necessity of induction in scientific method are right. But basically he fails, and basically nevertheless, science needs induction at a certain level, you will see, in a certain part of the scientific method. And for this purpose, I distinguish, and I did that already earlier in several papers, I propose to distinguish between three kinds of induction, three views of induction, right, concerning the role of induction. And by distinguishing these three kinds of roles of induction, I also distinguish between what we can learn from Popper's argument and from the critical rationalist, and what is exaggerated in this view and what is untenable in this view. So, the first view of induction is methodological induction. This is also what you see in this Aristotle's scheme, the inductive-deductive scheme, how it is often interpreted. Induction as a method of discovering general hypotheses, right? Methodological induction says induction is a method of discovering hypotheses, theories and laws. Right? As an example, so as a method of extracting them from observations. So for example, inductive generalization is such a method, right? If you observe that all our A's so far are B's, all of the observed ones, then you infer, well, probably the generalization is true. The next best general explanation for this observation is all A's are B's. And if that is falsified, I can revise it, right? But so long as it's not falsified, I conjecture it. So here, induction is a method of discovery. Popper says, this is his major criticism, well, but this is a confusion of the context of discovery in context of justification. If you infer from that induction is essential in science, for science, that is a confusion, because we know already, Popper says, that in the context of discovery, every method is allowed. Of course, induction is allowed as a method of discovery, but also trial and error, right? Like Kekule, who discovered his hypothesis about the benzene ring, as I told you, in a dream, right? So that's how Popper argues. So really, you don't need induction as a method of discovery. And he also argues what is very important insight, that scientific theories even are almost never discovered by pure induction. And this is already what I showed you just before, like Newtonian forces cannot be discovered by induction, because by induction only empirical laws which generalize the observations can be discovered, right? Kepler discovered his area laws by induction, which are saying that in a certain time the area which the planets move around the sun, the area between their trajectory and the sun, is a certain function of the time, right? It goes to the power of 3, right? With the time. So this is induction, but the inference to forces as a cause can never be discovered by induction, right? And here Popper is right. So theories are usually not discovered by induction, although we of course we have to admit empirical laws are often discovered by induction, but not necessarily, right? So induction is not really essential for science. It's not essential for justifying, for the question of justification. It's not essential to the rationality of science that induction is reliable. So that is what Popper says. Induction may be a discovery method, but that doesn't mean that the rationality of induction, the reliability of induction, is presupposed by science, right? Okay. Good. Next is logical induction. So the camp to which the philosophers' camp, the philosophical camp to which Popper was most opposed, were the inductivists. The empiricists and the inductive empiricists, so to speak. This was the group in the Vienna Circle, Carnap, who set up what he called the logical probability. Then Reichenbach in Berlin, who set up the frequentist probability theory, together with von Mises and others. And today, Bayesianism, which is a kind of epistemic probability account. And what is common to this very influential group of philosophers of science is the following. They regard induction as a method of justification. So here, Popper's argument against methodological induction doesn't apply to logical induction at all, because they regard induction as a method of justification, and as follows. Logical inductivists want to determine the conditional probability of a scientific hypothesis given all the observational data which we have. So this is the aim of inductive probability systems, right, of logical induction. So they want to come up with statements of this form: the probability of the hypothesis given the observations which we have is so and so. For instance, 90%. Now, for instance, they want to come up with statements like, if you really apply that, the probability that the Einstein's relativity theory is true, given all the observations which we have, right, is something like, say, I don't know, 95%. So this is what logical induction tries to achieve, and maybe at the end of this example you see already what the problem is, right? What would you say? What is the probability that the relativity theory, given all observation, is true? What is the probability? Is there any way, any reasonable way of determining this probability? Actually, in any case, no physicist, right, has at any time suggested such a particular value, right? So, I mean, you don't see how that can really seriously be estimated, this probability, the height of the probability, right? I mean, some people do it. For instance, some creationists have come up with the probability that God exists given all data which we have. And they computed a probability of 65%, and then the editor of the journal, the Skeptical Inquirer, which is a journal which is very critical against all these pseudo-scientific movements, set up another computation. He came out with the probability that God exists has a chance of 0.0 something %, right? But I mean, with the understanding that there is no really clear way of how we should come up with an assertion about the probability of the relativity theory. So, and this problem which I mentioned here, which I mentioned right now, is really it's the core of the criticism of Popper here. For what is the reason why we cannot really say what is the probability that the relativity theory is true? Because we can only come up with numerical probability value if we have a finite and well-defined. Maybe it need not be finite, but it must be a well-defined space of alternative theories or alternative hypotheses. We must have a well-defined partition. But in the case of theories, the range of possible alternative theories is unlimited, right? What are the alternative explanations of all observations which we have, including the observations which led Einstein to the hypothesis that the velocity of light is constant in all inertial systems, which then lead Einstein to conjecture that the time is relative, right? The time scale changes when I'm moving, and so on. But what is the best explanation of that? I mean, there are so many possibilities. You can introduce new theoretical models, you can introduce a new kind of forces. Maybe there's dark matter in the universe, maybe there's dark energy in the universe, maybe there are not 4 fundamental forces in nature, but 5 or 6. Right? So since you can introduce new theoretical parameters in your explanations, there is no limited space of possible alternative theories, and therefore you cannot measure the probability of a particular hypothesis, right? And that is what Popper said. What you can, by the way, is to say that a certain hypothesis is better confirmed than another one, in the sense that the probability of hypothesis H1 is greater than that of H2, given O. That can be done, right? That can be done, and if you investigate it probabilistically with much less assumptions, right? Probabilistically, you need to know the so-called prior probability of a hypothesis to come up with these values. And the prior probability is artificial because there is no space of possible alternative theories here. Therefore, you don't have any clue of the prior probabilities, how high they are. But for comparative assertions, you don't just have to, you only have to assume that the prior probabilities are approximately equal, or even if they are non-equal, they are not too far apart from each other. Right? That is all what you have to assume. So, Popper is right, even from a probabilistic viewpoint, that if you have a non-artificial, right, a more or less intersubjective acceptable assertion about confirmation and probabilities, then all what you can do is to say something like this: the probability of a hypothesis H1 given O is greater than the probability of a hypothesis H2 given 1. H2 given the observation. That is what you can say. You can say that the relativity theory is much better confirmed than Newtonian mechanics, because relativistic mechanics explains many more observations than Newtonian mechanics, but explains everything at least equally good what Newtonian mechanics explains. But it still even explains certain instances, certain observations which falsify Newtonian mechanics in addition. So it's clear that relativity theory, special relativity theory, is better confirmed, is more probable, given our empirical knowledge, than Newtonian mechanics. But it is not clear how high the probability value should be. And this is Popper's major critique, and here he is right. That is a major point. I mean, if you have a limited space of hypotheses, like when you deal with empirical hypotheses, then you can come up with probability assertions of that form. Like, for instance, your hypotheses are just how many % of people in Germany are brown-eyed? Up to 1% accuracy. So then there are 101 possible hypotheses. 0%, 1%, up to 100%, right? These are 101 possible hypotheses. And then, with certain mild assumption, you can come up with something. But in the case of theories, you don't have a space of possible hypotheses, and so you cannot measure. But you can have these comparative assertions here. So this is an insight which we can learn from Popper. But now let us think. If what we can really rationally infer from our scientific test procedures, that among the available and competing hypotheses, those are better confirmed than those. What does it mean? It means that so far they have been better confirmed, therefore we put more trust in them also for the future, of course. So what we of course infer is that you should apply relativity theory and not Newtonian mechanics to fast-moving bodies also in the future, because so far this theory was much more successful in explaining fast-moving particles than Newtonian mechanics, right? So what you assume is a principle which I call epistemic induction. And I'm fortunately, interestingly, not the only one, because independently from me, I then we discovered that some students of Popper introduced the same term. In particular, Alan Musgrave introduced the term epistemic induction. And there's another student of Popper, namely Watkins, who also agreed that epistemic induction is what is an ingredient of Popper's methodology. So epistemic induction is the following assumption. It can also be called meta-induction. You argue theory T1 has so far been more successful than another theory T2, therefore you believe that T1 will be empirically more successful than T2 in the future. Right? You believe it just, of course, revisably, right? For the time being. So in epistemic induction, or meta-induction as I call it, you imply induction, but not as a means of discovery, methodological induction, and not as a means of estimating the probability of hypothesis, logical induction, but as a means of transferring comparative evaluation of the successes of hypotheses in the past to the future. So you inductively generalize the observed successes among the computed hypotheses to the future, to the next instance, to your future action or whatever. If that would not be done or not be assumed, then the whole method of corroboration of the critical rationalist would have no points, right? Then if that would not be assumed meta-induction, then although so far the theory that heavenly bodies on Earth fall down when you let them go, right? And do not float freely in the air, although this hypothesis was much more successful than the opposite hypothesis, that sometimes or always the float freely. That would be no reason to suppose that that is still the case the next day, right? And so there would be no reason why you shouldn't jump off your balcony, right? Because So generally speaking, if the greater success of relativity theories and classical mechanics in explaining, in predicting fast-moving bodies would be not meta-inductively projected to our future action, then there would be no reason for the astronauts to apply relativity theory when they compute the trajectories of their space shuttles and so on, and then they would make false predictions, right? So that would be crazy. So meta-induction or epistemic induction is still something which is even assumed in the Popperian framework. But Popper himself did not really like it, this consequence. Some of his students accepted it, as I said, actually two very important ones. Popper spoke about this problem in his writings, but I think on personal reasons he didn't really like to accept the consequence that even in his program there's a certain kind of induction which is absolutely essential, namely epistemic induction. Well, however that may be, I think it is more or less convincing and more or less acceptable in philosophy of science that this kind of epistemic induction, at least, is that form of induction which is absolutely essential for scientific theory evaluation, for all methods of confirmation, test, right, and test, therefore, independent of the question of to which extent Hume's problem of induction is solvable, what we know is induction in the sense of epistemic induction is indeed an essential method in science. And that is what I wanted to argue in this part, in the last part of today's talk. What is following from that insight, that and from the insight that all what we can do is we can come up with comparative confirmation assessments and confirmation statements. It follows the degree of confirmation of a theory is doubly relative. So if I say relativity theory is greatly confirmed, is very well confirmed, then this is relative first, of course, to the current state of observable knowledge. This is clear, right? If I come up with findings in the future according to which maybe there exist particles which have higher velocities than light velocity, then of course relativity theory would be falsified. So that is clear. But this is also what the logical inductivist would say. The degree of confirmation is dependent on the current state of observable knowledge, because here you always insert the current state of observable knowledge. But what you learn from Popper here and from this criticism is that the degree of confirmation of a theory is always relative also to the current state of alternative theories, right? That because the current state of alternative theories defines, so to speak, your preliminary space of possible alternative hypotheses, right? And if you say it's very well confirmed, then you mean it's better confirmed than this and this and this and this alternative theory. But you can never say that maybe in the future someone comes up with a totally new theory, maybe involving some new theoretical terms, which is so much better than all theories which so far have been tested and so far have been conjectured, that from the viewpoint of this new theory, the probability of this old theory is now very low, right? So this is a consequence. Okay. So far, any questions to that part? Yes, please.
Yes. Isn't the real problem, which Popper pointed out, that you might have several or even an infinite amount of theories which are equally empirically successful, but you still might want to decide between the theories because maybe the future predictions will be different. And if you then want to decide, don't you need some sort of maybe intrinsic plausibility of these theories? That you, for example, say, okay, one theory says till the year 2014 general relativity applies, but afterwards it doesn't. This would maybe be a less plausible theory than the theory, okay, general relativity just applies throughout all time. And, and this would be why you stick to general relativity even for the future.
Yes, you can. That's right. Your last example is the problem of Goodmanian generalizations of theories, where you say, well, of inductive generalizations which are not inductive but Goodmanian, which have certain conversion points. So in sometime in the future, at a sudden, things behave differently, right? But what you generally said, that the true problem is that there exist infinitely many competing theories. That's not generally true, because if you are in the limited space of hypotheses consisting of probability assertions of a property in an infinite population, where you assert a real value, the probability is then a real number between 0 and 1, then you have exactly the case that you have infinitely many hypotheses, right, asserting that the probability of a certain property, the chance that an electron decays or an atom decays lies between 0 and 1, has a certain value R. There are uncountably infinitely many hypotheses now. But still, you can reasonably deal within Bayesianism with this thought, because this probability space is measurable. How is it measured? It's measured now by density, the probability, a P probability density function, dr. And that's exactly what all measure theory is about, right? Which mathematicians have greatly developed. So these kinds of infinite spaces are measurable. So the point is that the space is not measurable. You know, because you in theoretical, in theories where you have theoretical concepts, you introduce parameters, right? This hypothesis has only one parameter, x, and it says the mean value of x is r. But in theories, you introduce all kinds of theoretical parameters, right? And then, on that reason, the space is not measurable. The crucial point is that the space is not measurable in the sense of measure theory, and all that is infinite. So that's it. That is the answer.
Right. So, but even if there aren't infinitely many alternative theories, there might still be more than one. And
there are infinitely many theories.
Yeah, but in this case, but there might be cases where there are less. But we still.
But this point is agreed by you, right?
Yeah.
Yeah. So.
Yeah.
Good. So if there are only finitely many alternative theories, the space is always measurable. It's always measurable.
Yeah. But the question is which theory we might decide for And of course, I mean, we have abduction, the inference of the best explanation. In that case, the question would be, which one is the best explanation?
Yes.
How do we determine whether one explanation is better than another? And I think that is the crucial question, and maybe we need some sort of notion of what a good explanation is.
But for this, I must defend a little bit now the Bayesians and the logical induction. I mean, they have done great work. For this, the Bayesians would answer, we have the likelihood. Likelihood, this is just the probability, right, of the observation given the hypothesis, and at least under certain conditions, this probability can be estimated by means of relating degrees of belief to statistical probabilities by the so-called statistical principle, but which goes already far ahead now. But Bayesians have answers to that. Of course, you're right. In certain situations, even the question, what are the likelihoods, are unclear. But if the likelihoods are clear, the Bayesians would say, this probability is an indicator of the goodness of an explanation. The higher the likelihood, the better the explanations. Of course, then some inference to the best explanation theories, like Peter Lipton would say, well, but the likelihood is not enough. You have what he calls the loveliness of an explanation, and there's a controversy about this, right? But I don't want to enter this this debate here. What I wanted to tell you is that beside of these problems, you have the problem of measuring the space of hypotheses in the first place. And what Popper points out is that this, in the case of theories, the space is not measurable. So this is the most important argument, in my view. Any further questions? Yes?
Yeah, I'd like to get one step back and ask you to give one more example of a scientific theory that's not determined by induction.
You mean that is not generated by induction?
Yeah, without the
forces.
Induction.
Forces. That was my first example. You want a second example?
Yeah, I think aren't they determined by experiments?
No, you cannot measure forces. You measure them only indirectly by means of measuring distances or velocities.
But isn't that...
No, that isn't it. Certainly not. Think about it. Which experiment, by which... Tell me an experiment by which you measure the gravitational force. Right? Tell me one. And I tell you what you really measure and what is the inference.
Okay, yeah, the classic experiment is letting a stone fall from distance and then...
Yes, so what you directly measure is the time which the stone needs to fall 10 meters,
yeah.
Right? And you measure the distance, the velocity and the acceleration. But not the force. There is even no clue why there should be a force. Aristotle thought that there is no force here. For Aristotle, all bodies on Earth have the natural wish, so to speak, the inclination. They want to go to the center because that's the center of the universe. That's why they fall. There is no force here. The inference that there is a force is an abduction. So you see why the naive empirical model of science, I think you have in mind this empiricist view which the traditional empiricists had, that all legitimate scientific notions are directly coming from what you see and what you inductively generalize. Yeah, but that's not right. The major discovery of modern empiricism and philosophy of science in general was that these theoretical concepts cannot be extracted from observation because they go beyond what is directly observable. Right? The same with, well, all kinds of other, like magnetic fields, electric fields, all theoretical concepts. Do you see a magnetic field? No. I mean, if you have a magnetic, you don't just see that the particles are moving. Right? All force fields are theoretical concepts in physics. and so on. I mean, there are different kinds of theoretical concepts. Further questions? Yes?
I don't know, maybe this is too complicated to get into, but I was curious about why you think induction is not just a method of discovery, but also a method of justification.
Well, I can even give you a simple Bayesian answer, right? So, if you have a theory which has a likelihood, so it increases the probability of the observations, then this, by this you can infer that the probability of the theory given the observations now has increased compared to the prior probability. How high this ever was, right? If these probabilities are not 0 or 1. Even in this simple sense, so it gives you a slight probability increase, right? So it has a little justificatory value. That may be so little. I mean, you may come out that a reasonable degree of belief the prior probability P of t should be 0.005. And in your new space, probability space, where you have these new possibilities which you didn't think about before, right? This increase comes out as being minor. But still, that you can derive. If the likelihood is positive, then likelihood ratio, you call the relation of that and that the likelihood ratio. If that is positive, greater 0, then there's a little increase. So that is one way how you can argue that. But as I said, the justificatory value is minor. The major role of abductions in science are these intelligent discovery procedures. I would accept that, and I would not deny that at all. Further questions? So if not, then thank you for today. Until next lecture.